already said that W satisfies the partial differential equation that's written in blue, and so that whole equation equals 0. So if we're now adding the bottom line, the left-hand side is 0, because we've already said that W satisfies the equation that is 0, and that same equation appears on the right-hand side.
Right, so basically I think that derivation gets you, right, so this derivation gets you this formula, right? So if this constant, if dw dx times minus du dw times t is not 0, then the derivation here, sorry, if the constant is not 1, then the derivation here ensures that dw dt plus u times dw dx has to be 0, right? Yes?
In the third from the bottom line, dw0 dx, is that dw0 dt?
Okay, so w0 is, what it means is the solution at t equal to 0. It's the initial condition, right? So when you, for example, when you look into here, the solution is equal to, if you backtrace to t equal to 0, where is my x, right? So the solution would be equal to the initial condition at that point in space. So w0 is a function of x, not a function of t. All right. But it's a univariate function, so basically whatever I denote as dw0 dx is the derivative of that univariate function. There shouldn't be any confusion of notation here if I write d as opposed to partial. All right. Any questions over here? What happens when the quantity is actually equal to 1? Let me get back to you later. So that quantity, I think, is very unlikely to be exactly 1 all the time. If that happens to be 1 at a particular point, actually, is there something weird happening? I don't know. So we can look into that later. It's a good question, though. Okay, so this is the analysis of the behavior of this kind of a nonlinear hyperbolic equation. And the conclusion is that we have this kind of waves, still have waves going on in the space-time domain. And the wave still travels at constant speed along the line of travel, right? And these constant speed line of travel are called the characteristic lines. Okay, the characteristic lines are straight lines if the right-hand side is 0. If the right-hand side is not 0, these lines may actually curve. Okay, if the right-hand side is not 0, then basically the solution along these lines wouldn't be constant, but they follow actually a particular ordinary differential equations we can analyze. And because the solution is changing, the line may also curve. So this is kind of the behavior on smooth regions. But if you continue on this smooth region behavior, the characteristic lines, because they have different slopes, they may collide into each other. So next, let's analyze what happens when the characteristic lines collide. So to make things clear, it's good to use the example of the Burgers equation, dw dt plus w dw dx equal to 0. In here, the u is equal to w, right? If we draw the space-time domain, and let's actually imagine the initial condition being a sine curve. So if this is 0 and 1, what is if I have a sine curve, then this is the top of the sine curve, this is the bottom of the sine curve at t equal to 0, right? And now this is halfway, which corresponds to a 0 solution. So for a 0 solution, what is the characteristic, what is the speed of the characteristic? And what is the shape of the characteristic going to look like? It's going straight up, right? U is equal to 0. So minus u times t is equal to 0. So I have a fixed x. The solution along this line should stay the same. How about at x equal to 0 and 1, which is the same point? Well, the solution is 0 again, right? So on these ones, I also have a characteristic going straight up, which means the solution at 0 and 0.5 and 1, they are going to stay equal to 0. That's not the case for 0.25. At 0.25 and 0.75, the solution are positive and negative respectively. So in which direction is the wave going to go? Well, at 0.25, it's going to go towards the right. At 0.75, it's going to go towards the left. What's happening now in these points? On these points, 0.18 and 3/8, right? If you look at the sine curve, the solution are still going towards the right, but at a lower speed, right? So at a lower speed, it's going to be like that. And here, the solution are still going to go towards the left, but also at a lower speed, something like this, right? So, and in between, you can kind of interpolate. So we have a collection of characteristics that looks like that. All right. Okay, so this is what happens in a smooth region, but at some point they are going to run into each other. And when you run into each other, there is a discontinuity that is going to be created. And this equation doesn't really make sense anymore. Does it? Okay. The reason it doesn't make sense anymore is that I don't have any derivatives. So what does it mean by having a solution to this differential equation? We have to actually redefine the differential equation in order for it to have a meaning, right? It's just like when you have a Gaussian function that becomes sharper and sharper, taller and taller, and the narrower and narrower, it converges to a delta function. But the delta function is not a function, right? So you have to define a function in a weaker sense, in a more general sense, for this to mathematically make sense.